All right. Okay. Okay. So let's get started. Today is our eighth uh, OSU ALT seminar series. We are more than happy to have Javier from Microsoft to give us a talk today. So let me give a brief introduction about Javier. So Javier is a managing director of research for industry and the CTO of Agri-Food at Microsoft. He also leads the networking research group at Microsoft Research Redmond. Previously, he was the chief scientist at Microsoft Azure Global. Javier is a well-known researcher in the networking and system research community. Not only for that, his research has been shipped as many parts of the multiple Microsoft products. Particularly, Javier started this very well-known project called FarmBits at Microsoft back in 2015, and we're gonna hear a lot today about this project. And this particular project was featured by Bill Gates in Gates Notes. Javier is a fellow of the ACM as well as the IEEE, and has won many awards, for his research work, including many best paper awards, including ACM Mobicom 2019, Microsoft Gold Star Award, MIT Technology Review's Top Innovators Honor 35 back in 2010, and many others. So without further ado, I will give the floor to Javier. Thanks again for giving us a talk today.
Thank you, Mi and Anish. And Mi, that introduction was, that was a long introduction. Thank you for going through it. So I'm really excited to be talking to all of you, and mostly to get, in addition to telling you about what we are doing, also to get feedback. And we are doing some work with Ohio State University, especially on with the agriculture department, and would love your thoughts on that as well, and explore potential collaborations with the department, because we are just scratching the surface. So let me just start by telling you about what is this problem? What are we trying to do? So we're trying to address the world's food problem. So before I go there, I just wanted to give a little bit more background to what you already mentioned. So yeah, my PhD is in computer science, and like many of you in the audience, but and it's not in agriculture. Yet I started this project. The reason I started this project is I did spend a lot of time growing up in India, in one of the rural parts of. So I grew up in Jamshedpur, which is a city in eastern part of India. But a lot of time I spent with my grandparents, which was in Bihar. It's a state in the northern part of India. And back then, I did not like anything to do with agriculture. You'll be like, man, why did you start this project if you didn't like agriculture back then? The reason I did not like anything to do with agriculture is, so the reason I would have to go there is, as it used to happen, my parents would drop me off at my grandparents' place, and it was me and my brothers and sisters. We would be spending our summer and winter vacations there. These villages, they did not have any electricity. They did not have toilets. So it wasn't like rest of the time, like 8 months you're in a city and 4 months you're there. It wasn't the best time. Although I did make a lot of friends, learn to bicycle and all that with those friends there. But it wasn't the 4 months I would look forward to. Yet, those times exposed me to a lot of poverty, a lot of very primitive forms of agriculture. Like I remember one of the things my mom used to do is she would do the prayers and leave the offerings outside the house, and there would be a swarm of people and kids just trying to grab anything to eat. There is that much poverty in that region. And that was one of the things that has stuck to my mind. And so since I graduated, joined Microsoft, even though quite a bit of my work has been focused on shipping products, I always try to do one longer term project along with the more near term things that ship as products or advanced computer science. So one of them was this space. But the problem here is much bigger than just the problem that I was talking about when I was growing up. The world needs more food to feed the growing population of the world. And it is not just about growing more food. Just to give you a perspective, the estimates say by 2050, you need 50% more food compared to today's levels. It is, and you need to grow this food, even though there's not much more arable land. The soils are not getting any richer. The water levels are receding. There's climate change. And it is not just about growing more food, it is about growing good, nutritious food. So how do you grow this good, nutritious food without harming the planet? And that's the fundamental problem that we are going after. It's like previously the world faced such a problem when there was the Green Revolution back in the 60s and 70s. We are at that position again. So our vision there at Microsoft is one of the approaches that can help us get to this goal of sustainably nourishing the world is that of a data-driven agri-food system. What we mean by a data-driven agri-food system is if every entity in the agriculture and food supply chain, from the seed companies, the tractor companies, the farmer, the warehouses, the logistics companies, food processors, retailers, consumer, if every entity could start using data and AI, this could drive significant efficiencies in the entire food supply chain. The numbers here are actually from a close partner that we work with. It's based out of Chicago. It's S2G Ventures. And these numbers show how much improvement is possible. But in fact, if it is not just about each entity adding more efficiencies, if each entity could start sharing the data across the entire food supply chain, it could lead to even more efficiencies. It could lead to new business models. Things like, if you could know as a consumer which farm a particular food came from, it could drive various transparency scenarios like track and trace. If something goes wrong, if there is contamination, you know which farm it came from, you can immediately withdraw all the food from there. It leads to new scenarios around nutrition. Like many of you might have heard about the recent issues with chocolate, which were contaminated because of where it was grown. It could lead to new scenarios around sustainability. Like, some of you might be paying more for organic food. Would you pay more for sustainably produced food? That the farmer is doing the right thing for the planet. There's no child labor used in growing that food. These are all new business models that could be enabled if you could start sharing the data across the entire food supply chain. So at Microsoft, we have been working on various aspects of this entire food supply chain. Today, I'll talk more about the first one, which is on FarmBeats and FarmVibes, about data-driven agriculture. The other two things, which I won't talk much about, but I'm happy to answer questions. The second one is on the food supply chain transparency, that is FoodVibes. That's the question I was talking about. That is, how do you capture information and transfer that information through the entire food supply chain? Many of you might think blockchain is the answer. Well, blockchain is one part of the offering, but the bigger problem we think is what do you put in the blockchain? And how do you do one of the issues we face there is we think it's the first mile of the food supply chain. That is, a lot of information is lost from the time the food is harvested or the produce is harvested in the farm to the time it leaves the farm. And the challenge is, you could tell the farmer, do this, do that to digitize, but the farmer is not most tech savvy. So the particular thing we are trying to do here is build a hands-free digitization in the first mile of the food supply chain. There is other work we are doing here in the second pillar in FoodVibes as well. One of the technologies that the team has invented here is that of carrying information in the DNA of material. Like the apples that you buy or any produce that you're buying, they're coated. They're coated to make sure that they don't ripen in advance. What if in that coating that they put on the apple, you could encode information in the DNA of the coating to transfer that information through the food supply chain? There is some new work that's happening in that space. In another work around the second pillar, there's work happening in the knowledge graph. That is, can you model the entire food supply chain as a knowledge graph, as a large model, and then use that to reason about things? Things like, if there is a drought in Chile, how will that change the price of apples in Ohio State? So these are the kind of questions that we're looking to answer as part of the second pillar. And the third pillar, what you're seeing here, is on modern R&D. Essentially, what we're saying is that how do you help food production further downstream? Like, for example, the food that you're eating, the food processing that happens, can you come up with nutritious ingredients so that the food that you're eating, we also do things like alt proteins, like, the food that you eat from, some of you might be buying food like Impossible Burgers or Beyond Meat. And this entire space is proceeding at a very fast pace. So one of the things the team has been working on is how do you accelerate the invention of new food types? But I won't talk about these two anymore in this talk. If there are questions, we can cover later. But I'll talk about the first one. How do you enable data-driven agriculture? So, one of the things with agriculture is that it's also very deeply tied with climate change. Agriculture is one of the biggest emitters of greenhouse gases. In fact, the entire agriculture and food supply chain account for about a quarter of the greenhouse gases. It's not just carbon dioxide, it's also nitrous oxide from a lot of fertilizer that is put in the farm. It's also a lot of methane from livestock and from other sources. Agriculture is not only one of the biggest emitters, it's also one of the most impacted by climate change. That is, if you think of farmers, they rely on predictable weather for every decision that they take. When should you plant? When should you harvest? A lot of those decisions, they rely on predictable weather, predictable climate for that region. So agriculture is not just one of the biggest emitters, it's the most impacted, but more interestingly, agriculture could be one of the solutions for climate change as well. That is, if agriculture is done right, using the right agricultural practices, it can pull some of the carbon from the air. It can pull some of the carbon and put it back in soils because of photosynthesis. As you know, plants, they would take the carbon from the air and convert it into oxygen. And the more plants you have, the more trees that you have, and you use the right agricultural practices, some of that carbon might go back into soils. So the question is, okay, how do you then drive the adoption? How do you help farmers know what's right for their farm, how much the emissions are, not just how much the emissions are, how do they adapt to climate change, and how do you sequester more carbon in soil? One of the approaches that we started working on back in 2015 is what we call data-driven agriculture. With data-driven agriculture, you could map every farm in the world, like what you're seeing here, and overlay this with data. For example, what is the soil moisture level 6 inches below the soil, below the surface? What's the soil nutrient level? What's the soil carbon level? If you could build accurate maps like this, it would enable techniques such as precision agriculture and regenerative agriculture. And if you could do precision agriculture, like, you could put water only where it is needed, you could put chemicals only where it is needed, you would put only much less fertilizer, it could help improve yield. That is, you could grow more in that farm. It could help reduce costs. That is, if you put less chemicals, if you use less water, it saves cost. It's also better for the environment for the same reasons. You're not wasting water. You're not putting in more chemicals that are needed. Just to give you some idea, I'll talk about that farmer later, but one of the farmers who's been using some of the techniques I'll talk about today is using less than 38% chemicals in his farm, which he farms around 8,000 acres. And for that farmer, it's a huge cost saving, and it's also better in terms of the climate impact. The thing is, even though data-driven precision agriculture as a term is not something that we came up with, precision agriculture, what precision agriculture means is you apply inputs only where it is needed in the farm. So right now, most farmers, what they do is they'll apply chemicals uniformly throughout the farm. They'll put water uniformly throughout the farm. With precision agriculture, if you have maps like the ones I was showing previously, you would apply water only where it is needed. You'd apply fertilizer only where it is needed. The thing is, precision agriculture as a concept was proposed back in the 80s. It's been a long time since it was proposed, more than 40 years. The thing is, the technology still hasn't taken off. And the biggest reason this technology is not mainstream yet is because of still the high cost of these existing data-driven agriculture solutions. Just to put this in perspective, when I started this project, I started working with a lot of land grant universities. One of the universities we started working with was UC Davis and University of California, Davis. It's a very good agriculture school. I went there in 2017 to one of the expos that was going on, and there were lots of precision agriculture companies, a lot of ag companies presenting the latest and greatest ag tech equipment. Even the cheapest, just the sensor part of it, it's more than sensors, right? But just the sensor part of it that was available there, the cheapest one was 5 sensors for $8,000 and a recurring cost. You would think, hey, I could just buy a sensor of Amazon for like $10, a soil moisture sensor, but it's more than that. These things have to be ruggedized, have to be battery operated, have to work in remote areas where there is no connectivity. And because of that, at 5 sensors for $8,000 and a recurring cost, the ROI, the return of investment for the farmer is not there. What do they get by putting a few sensors in the farm? How would they even recover the value for the 5 sensors? So that is what when we started this project, that was the vision of the project. Can we significantly bring down the cost of precision agriculture equipment, the total solutions we are thinking of, by 2 orders of magnitude? And I'll talk about a few ways in which we believe we can get there. So the kind of innovations we've done, but this is just scratching the surface. So the number one reason why existing solutions are expensive is because of connectivity in the middle of the farm. The farmer's house, especially in places like the US, the farmer's house typically has some sort of connectivity. They won't have broadband. They pay for broadband. What they get is 1 to 3 megabits per second connection. But the bigger problem is that the farm is a few miles away. Even though sometimes you could get connectivity even when you plant the seeds, by the time the crops grow, the connectivity is gone. And it's more than that. In fact, there was a study by the USDA less than a couple of years back, which said that around 60% of US farmland doesn't have good internet connectivity. And this is the problem here. The problem is even worse if you start going to emerging markets. So there was a recent paper I wrote in the communications of the ACM with Stuart Collis from the Gates Foundation, where we looked at this problem of digital agriculture for smallholder farmers. And one of the things we found was that just to give some statistics here, around 40% of it's slightly less now, it's like 38% or something like that of the world's population is still not connected to the internet. We take internet for granted. But at the same time, if you look at the GSMA reports, they say that over 90% of people are in coverage area. The thing is, even though it is in coverage area, there is like 30% of the population that is still not connected because the connectivity is not affordable. So that's one problem we need to solve. We need to bring affordable connectivity to the smallholder farmers worldwide. The other problem, it's not just about connecting the farmer, it's about connecting the farmland, which could be in remote areas, and that is a much bigger problem as well. So then the question is, how will you bring connectivity to remote sites? One of the solutions that I have been working on for a very long time now, and there is work that's happened in Ohio State as well, and there's work happening in other places too, and our community has contributed to this, is that of TV white spaces. So for many of you who might not know this technology, the idea is the following. What if you could take a Wi-Fi signal and put it in empty TV channels, right? Just a hypothetical. So like when we started, that was hypothetical. Now it's real. So the way it would work is if you could put, say, in this case, TV white spaces base station on a grain silo or in a farmer's house or office, you could get miles of connectivity around it. Just to give you an idea of what this enables, right? Suppose right now, what if you could take a Wi-Fi router and you can access it a few miles away? That would be cool, right? Right now, as soon as you leave your building, the Wi-Fi disappears. And the way we did that was we took a Wi-Fi signal and we put it in empty TV channels. And once you did that, you could then access it really farther distances. The reason is that, compared to Wi-Fi in 2.4 gigahertz, in UHF bands, you get 4 times the range. In VHF, you get 12 times. This is just based on physics, right? Free space and size of antennas. But the thing is, the interesting thing here is that in the middle of most of the TV channels, the TV towers are in cities. You have TV towers in Seattle, you'll have them in Columbus. The farm is away from the cities. If you turn on a TV in the middle of a farm, most of the channels is just white noise. The more empty channels there are, the more bandwidth you could get in the middle of the farm. So even if you have 20 TV channels, you're talking of in the US, 120 megahertz of available spectrum, which you can then start using to connect all your devices in the middle of the farm. So this is one of the technologies that we are looking at. Just like Wi-Fi connects your house, this technology can be used to connect your entire farm. You buy this router, put it in, put an antenna, and miles around it gets connected. In addition to this, we are also investigating other technologies. One of them is around private 5G. So, just like you have a 5G base station, can you just take a similar edge device, run all the 5G stack on this edge, light up a tower, and then you get 5G connectivity in the middle of a farm? The other thing we're looking at is space connectivity, low-cost space connectivity. So can you then use, one of the things we did was we worked with a partner to launch an IoT satellite. And you could then connect your LoRa devices directly to space and then use it to provide connectivity. So we are looking at multiple tech, but the underlying thing I wanted you to take away is that when we talk of data-driven agriculture, the number one problem we need to solve is connectivity in the middle of the farm. Without connectivity, all the other scenarios don't really light up. Like a second challenge is that of sparse sensor deployments. That is, I talked about maps like this. Suppose I gave you the challenge. I took you to one of the research farms at Ohio State, and I asked the question, what is the soil moisture level 6 inches below the surface, that is at the root zone, for example, throughout the farm? if we ask soil scientists this question, that is, you have to build an accurate map. Well, the answer will be, you need a sensor every 10 meters because soil moisture varies from row to row. Well, that is what the soil scientists would say. Putting a sensor every 10 meters is expensive to deploy, to manage. It will come in the way of the farmer as the farmer does the day-to-day job. So instead, what people do right now is they'll take samples, say one of every few acres, and then they use Craiging's method. So Craiging's method is basically, if this is point A, this is point B, everything in between is in that region. Craiging's is slightly more advanced. It says this is Gaussian, every point is Gaussian, and use that to do the interpolation. But those are known to be very inaccurate. So instead, we ask the question, can we build a more accurate map using a sparse sensor deployment? So our solution was to use aerial imagery and use multimodal AI. Essentially, what we do is we first use either drones to cover an entire farm. You create these images like you're seeing in the middle of the entire view, create a 3D point cloud and a really good view of the farm. If you don't have drones, we have another technique that we built called, this was using tethered balloons. That is, if I wanted high-res imagery, what we did was you could get a big balloon, like a 4 to 5 feet balloon, which is tethered to the ground, goes up 150 to 200 feet. What we built was a weatherproof mount where you could put your smartphone with your camera facing down and a battery pack attached to it. And this thing could stay up for 4 to 7 days, taking images of the farm. If you take it to emerging markets like in India or sub-Saharan Africa, where labor is cheap, someone could just walk around with the balloon. And then what we did was we had computer vision and ML algorithms to stabilize the imagery to then build these accurate maps of the farm. This paper got one of the best papers at ACM Compass, where if you see Bill Gates's video on Gates Notes, he's also walking around with this. This is one of the things we are working on for low cost, for emerging markets. In fact, Bill had a very interesting idea when we showed him this. He was like, well, you're using helium for this. What if in these farms, there's a lot of methane because, especially if they are cows, and you tap into methane to get these balloons up. The interesting challenge there is, you could use methane, but they're inflammable. So that's something we need to think about. But that was an interesting idea. We're still thinking about it. But in most farms where you don't have drones or balloons, what we use is satellite imagery. We use satellite imagery to create these kind of images. We then have an AI algorithm using which we decide which are the best places to put sensors in the farm. Essentially, we use segmentation and then some intelligent segmentation based on the multispectral or hyperspectral imagery to decide where do you put sensors in the farm. Once you put the sensors, what we essentially do is then we build an ML models to do the interpolation. Essentially, wherever you have sensors and you have the imagery, then based on what you're trying to interpolate, we look at what bands there is, suppose it's pH or nitrogen, and we use that to build a model. And then we use the trained model to then predict these values in other parts of the farm. So we've done this for soil moisture, soil temperature, soil pH. Now, most recently, we did it for soil nitrogen and soil carbon, and we got very good results for those as well. So one of the challenges, though, is, once you start taking satellite images, around 70%, more than 70% of satellite imagery is cloudy. So if it's cloudy, you really can't see anything which is happening below the clouds inside. Like anything you're seeing on the left part of this video that's playing on the right, this left part of the video is what you get right now. With SpaceEye, what you're able to do is create the images on the right. That is, you can see when the farm is tilled, when the farm is irrigated, when the emergence happened, all of that stuff on the right. And the way we do that is, this was done by one of my interns from MIT, who's now at UPenn. He's a professor there. Mingmin, what he did was, he looked at another satellite that goes around the Earth that has radar in it. Radar signals, they go through the clouds and reflect differently from different surfaces. And then based on the radar signals and using neural attention on this cloudy imagery, we are then able to predict what's happening below the clouds in satellite imagery, and with a very good accuracy. The accuracy was over 95% for 3 of the 4 seasons. Snow is where snow and clouds become tricky in the winter season, but for everything else, we are able to do this and see what's happening below the clouds in satellite imagery. The third challenge is, I talked about how using the TV white spaces, you can bring connectivity, low-cost connectivity, or using space IoT and others. The second challenge was about how do you reduce the number of sensors needed in the farm using AI. The third challenge was, I talked about how you could get all of this data, but the connectivity from the farm to the cloud is weak. Many farmers, they pay for broadband, but all they get is, say, 1 to 3 megabits per second of connection. Every time you fly a drone, like in a 15-minute drone flight, you're generating like 3 to 4 gigabytes of data. shipping 3 to 4 gigabytes, and that too, I'm not using like a fancy hyperspectral camera. Like if you have 3 to 4 gigabytes over a 1 to 3 megabit per second connection to the cloud, it will take forever to send all of this data. So instead, our key idea was that, most farmers, they have a PC. If they don't have a PC, we'll ship them a PC form factor device that sits in the farmer's house or office and does a lot of compute sitting in the farmer's house or office. So everything you're seeing in this big gray box sits in the farmer's house or office. It gets data from sensors, it gets data from drones, you do the orthomosaicing, the panorama generation, the heat map generation I talked about. Everything is running in the farmer's house or office in that computer. We also have this last column of services. This is not something we do. We are not the agricultural experts. This is something that is done by our partners who are experts in academics or partners who are delivering things to customers. We also ingest data from cameras, say over the TV white spaces coming to this edge device where we do deep learning on the edge. All of this data is lazily synced with the cloud. It is this was a Mobicom paper a couple years back where we came up with intelligent compression technique to send all of this data, large amounts of data, using a progressive compression technique where we look inside the image and see parts of the image that are more important compared to the other parts of the image and use that to prioritize which parts of the image are sent. This edge device also has a web server so that even when there is no internet connectivity, you could still access the data and the intelligence sitting on the edge device. So then just to talk about how, so the fourth challenge we have is that of tech savviness of farmers. Most of the farmers, they're not very tech savvy for multiple reasons. In the US, one of the challenges is that of the growing age of the farmer population. That is, the younger farmers don't want to stay into farming, the children of farmers. They'll go to the city. So what has happened is the average age of a farmer in the US has gone up. And this is not just in the US, this is happening in the emerging markets as well. Like the farms I talked about, where I spent a lot of time growing up, the friends I made, they are not farming anymore. They'll go to a city, they'll pull a rickshaw, they'll work in restaurants, but they won't farm. It's, they just feel that's the next stage of their life. And what has happened is that the average age of the farmer has gone up. If the average age of the farmer has gone up, these are not the farmers who are most tech savvy, typically. So what we are doing here is we're looking at taking some of the latest innovations that are happening around large language models and ChatGPT to create a large language model interface for farmers. So what we are doing is, instead of a farmer, and the other challenge is that, in addition to the aging population and the lack of tech savviness of the farmers also are in the middle of the farm, their hands are dirty, their hands are soiled. You don't expect them to be using a phone. One of the things we've done is open up a speech interface so that, with speech, using speech to text, and then text to text in any language, a farmer can then start communicating with all of the data and insights that we are able to generate using, for example, the previous technologies that I talked about. So now coming to how the farmers are using this stuff, we've deployed this in multiple farms, all the way from a small farm of 0.5 acres to large farms of 9,000 acres. And I'll talk about a few of the use cases. So one of the things we do, this is a KDD paper from a couple of years back, where once you put a sensor in the ground, we not only tell you what the sensor values are right now, but we'll predict what the sensor values are going to be up to 5 days in advance. What you're seeing on the bottom right is two of these graphs for soil moisture and soil temperature. If you look at the red bar, even up to 5 days in advance, the error is less than 8%. And the way we do that is we took weather station data from across 50 weather stations across Washington state. In this case, we trained that model based on that 50 weather stations. And then we start making very hyper-local predictions for any sensor you put in the farm. And at the bottom left, you're seeing one of the testimonials from a farmer in Eastern Washington. There was a part of the farm where he found was heavily infested with weeds. He was going to spray chemicals in that part of the farm. The weather station prediction was it was going to be 42 degrees. We predicted it was going to be 31 degrees. It was 30 degrees. This is below freezing. It was good he didn't spray chemicals, otherwise he would have lost his crop. So the key idea here, the way we do that is, we look at the weather prediction at the weather stations. We use that to then create a wavelet transform. We look at these patterns. And then once you put a sensor, we look at how this correlates with the values at the weather station, use that to then start making very hyperlocal predictions for what's happening in the farm. There are other use cases of this too, like this farmer He farms 9,000 acres spread across 45 miles. Every time he takes his tractor out, his tractor is going to spray chemicals. He wants to know what the wind prediction is in different parts of the farm. So with this, he can see them during the day, how the wind is going to be in different parts of the farm and use that to plan his route so that his spraying is most effective. This is another use case I like talking about. This is a farm in upstate New York. The farmer wanted to know, this is a 4-kilometer stretch. The farmer wanted to know how his cows are doing once they're out in pasture. So what we did was we flew the drone, we transmitted the data over the white spaces to an edge device, a computer sitting in the farmer's house or office, where within 30 minutes, we were able to show this beautiful map and start overlaying with data. For example, from left to right, the grass is growing back well. There is a water puddle that needs to be fixed before the next planting season. The cows are pooping well, which is also important information for the farmer. This is deep learning on cow poop. So this was done by one of our interns. We don't make our interns, all the interns look at cow poop, but this particular intern was really fascinating, really built a really cool algorithm for this. This is where the cows are. This is a stray cow that needs to be herded in. All of this within 30 minutes of flying the drone. This is a farm close to Microsoft campus where we take a lot of visitors. If you see Bill Gates' video, this is a farm he shows in that video. We show the farmer these beautiful pictures and we overlay this with data. For example, at the bottom left part of the farm, we were able to flag that is moist, even though we did not have a sensor over there. This is after the farmer had applied lime, we were able to flag that the black parts of the farm are still acidic. The farmer needs to reapply the lime before planting the seeds. So there are many other use cases, and there's the farmer here, and I could go talking about various other scenarios. Like we recently did another study with the farmer in Eastern Washington. He actually talked about the different stages of farming, all the way from planning to planting. Actually, this is still related to this. From planning to planting to production to harvest to post-harvest. And each stage, he talks about all the ways in which data and AI, the technologies that we're building, has helped him. So going back to the first issue I talked about between agriculture and sustainability and how is all this related to sustainability, I want to talk a little bit more about what Microsoft is doing in this space. Microsoft, in 3 years ago, we made a big sustainability commitment. We said, especially around carbon, we said that by 2030, we are going to be carbon negative. And we are going to, by 2050, we will remove all the emissions we'll ever generated since the time Microsoft was founded. What do we mean by carbon negative? By carbon negative, we mean that we'll be putting back more carbon than the amount of carbon that we generate. That's a big, bold ambition. So we also made other very important commitments around waste, water, and biodiversity. But around carbon, one of the questions is, how will we get to carbon negative? So one of the initial analysis we did was we said, one of the ways we get there is by reducing our own emissions. That's the blue curve we are seeing here, but that's not going to be enough. We need to offset our emissions using other techniques, other technologies. So we're purchasing carbon. So, a couple of years back, we started by making the biggest corporate purchase of carbon ever. We purchased 1.3 million metric tons of carbon. And out of that, 100,000 metric tons was from soil carbon, from Land O'Lakes. And so we've been working on, so the thing is, with agriculture, this is one of the ways in which you could pull carbon from the air and you could put it in soil. There's still many open questions, and we are taking that into account and working with scientists as we are looking how do we get to meet our sustainability goals. So towards that, one of the platforms we built is Project FarmVibes.ai. This is essentially what we are doing is we are taking a lot of data, ingesting that. So I'll briefly first talk about what we did with the first phase of the project, which was Project FarmBeats, which 3 weeks back, I was on stage and we announced this product called Azure Data Manager for Agriculture, which is what Project FarmBeats has become. Think of that like a data platform for agriculture. And on top of that, we built various AI workflows for sustainability, which we call Project FarmVibes.ai. As part of the AI workflows, there are a few things we are doing. First is we are doing curation and preparation of data. So bringing the different data types, doing the data fusion, like for example, the SpaceEye technology, bringing in data and cleaning it, we do that. The next part, what we do is we have a lot of workflows for labeling and training the data. And then we also, in the last phase, we actually take that to insights and make predictions. There are multiple workflows that we've released as part of this platform. Just to walk you through, so this is all open source, by the way. I would definitely recommend you to try out Project FarmVibes.ai and contribute if possible. This is all on GitHub if you go there and check it out. This is just one example of what we're doing here. Suppose the question that you wanted to answer was, how much carbon is sequestered by the amount of wheat farms growing across, say, Washington state. So you would then build a workflow. You'd say, I need satellite data, I need other data. Then once you get the data, I need to label that data. Once I get that label. So the first thing you'll do is you'll say, okay, let me detect all the wheat fields in Washington state. And for that, the way you do this is go to, these are all workflows in there for crop detection. You would say, go there and detect all the crops. One of the other things you can do is on top of that, you can say, I want to do the canopy cover workflow. What you're seeing here, fractional canopy cover is a good prediction of biomass, also of yield. These are all you can say, okay, now I want to run this workflow and plot a time series for that. And once you plot these time series, this is all these are workflows that already exist. Once you do the work, once you plot these, the time series, say of canopy cover or for other such parameters, you can then start looking at various management events that have happened in the farm. When did irrigation happen? When did harvest happen? When did germination happen? You can start seeing a lot of those events. One of the other tools we built is a what if analysis tool. You can overlay that on a satellite image. You can draw a polygon for a map. On the right, you can give it a lot of statistics because, a lot of times farmers, we tell farmers you should do this, you should do that, but they're running a business. They need to know that if they change their management practice, like for example, the harvest date or anything else, how will it change the amount of carbon in the farm? So here, for example, you could create your farm, you could give it all the inputs, what you're planting, what is the fertilizer, you can change these dates, and you can see how will it change the amount of carbon. You can also have similar workflows for yield prediction. So in the end, a farmer can take more informed decisions about what they should be doing in the farm. In addition to showing it on a map, we also have Power BI workflows. You can go and say, okay, now plot it as a Power BI. I want to see for this particular farm. I want to see for carbon, plot it as a time series, plot it as a Power BI visualization so that I can see what the impact is and take appropriate decisions. We are also working with multiple customers. For example, Land O'Lakes, one of the questions Land O'Lakes asked, this is related to Ohio and Iowa. They took data from Iowa and said, in Ohio state, what are the practices that farmers are using? So one of the ones we looked at was with terraces and grassed waterways as two sustainability practices. So Land O'Lakes wanted to know which farmers are using what sustainability practices. If you just use satellite data, it's not going to give you good results. The accuracy was not quite good. So again, one of the key things with FarmVibes.ai is it supports multimodal AI. So we took data from NAPE imagery, which is 1 meter resolution USD imagery, along with the digital elevation map, which we use as another workflow. And then we are able to predict this accuracy at over 86% accuracy, compared to close to 60, I think it was 68 or 70% earlier. So significant improvement in accuracy using multimodal AI and the workflows that we've released as part of Project FarmVibes.ai. So as I was saying, this is all open source. I would love for you all to try it out and give us feedback. The team is very, very responsive. If you want to use it in a class, if you want to use it it's with the MIT license. So there's a lot of things you could actually do with this code, and would love feedback as well. One of the other things I talked about, what we are doing from the product side, from research to taking things to open source, working with customers. We're actually doing more than that too. We're working on the societal side as well. One of the things we did was we created a FarmBeats student kit, and now we've integrated the FarmVibes workflow on top of that as well. So some of you might be getting confused as to what is FarmBeats, what is FarmVibes. Think of FarmBeats as a data platform. That is, how do you get data from the middle of the farm? And FarmVibes is everything on top about insights, translating that data and writing AI on top of it. So one of the kits we built was basically we took all of that and worked with the Future Farmers of America, the FFA, which works with a lot of farming high schools, for example, rural high schools across the US. We then created a curriculum around it, and we partnered with the FFA through these FarmBeats student kits with the curriculum to train the high school students in these rural communities with data and AI. So there are multiple reasons we did this. One is we wanted these remote high schools to be trained in data and AI, but we also wanted them to see the applications of data and AI in farming. Additionally, I think one of my personal goals here is that, through this, I hope that this can make agriculture cool again. That is, as I said, a lot of the younger farmers are not staying into farming, but if they see all the latest in AI, in technology, in drones, in robots, everything being used in farming, a lot of the younger population might actually stay around and do farming again. So that's it. I wanted to conclude. I know many of this is a research audience. So I wanted to conclude with some of the other tech that we are still in research stage that we are working on right now. So as I said, we're still scratching the surface in enabling this true vision of what we call democratizing data-driven agriculture. Our vision is that every farmer everywhere in the world should benefit from data and AI. They know a lot about the farm. They should be able to use data and AI as part of their daily operations. To get there, I think right now we kind of understood what to do for medium to large scale farmers. But to take this to smallholder farmers will take we need to solve some other hard problems. One of the problems we are trying to address is that of affordable sensing. This was the paper that got the best paper runners up in ACM Mobicom recently, which is work with one of my interns who was at Rice earlier, and now she's at Yale. What we are looking at is, I talked about the cost of sensors, and the cost of sensors is still very, very high. As I said, if you wanted to get a good soil moisture or electrical conductivity sensor, it costs a lot of money. It costs a few hundred, if not $1,000. Most farmers, especially smallholder farmers, they won't spend $1,000 for a sensor in the farm. Even though they won't do that, a lot of them have a smartphone, even if it is a very low-end smartphone. If it is a smartphone, it has a Wi-Fi chipset in it. If it has a Wi-Fi chipset in it, the key idea we had was that if you have a Wi-Fi chipset, if you could measure the time of flight of a Wi-Fi signal from the smartphone to another point, the time of flight depends on the permittivity of the material. The permittivity of the material changes by, for example, soil moisture. If you could compute the time of flight, you could then start inferring a lot of properties about soil. The challenge is this time is of the order of nanoseconds, and measuring it is super hard. The other insight was that most of these Wi-Fi chipsets, they have multiple antennas. If they have multiple antennas, then rather than measuring the absolute time of flight, you could measure the relative time of flight. And if you could do that, you could then start building a very low-cost system to measure soil moisture and soil EC. So we built this, and we showed it. In fact, the Gates Notes article that was written, the title was "Can the Wi-Fi in your phone help feed the world?" So this is what we are after. If we can enable anyone with a smartphone to go measure soils, it can then light up. It can then be a big step towards democratizing data-driven agriculture. A farmer anywhere in sub-Saharan Africa can then start knowing what the soil properties are. So I was giving this talk actually right before COVID. This was the last trip I made in 2020 in March, when I was in DC at the National Academies. I was giving this talk, and one of the people in the audience was Professor Ratan Lal from Ohio State University. And Professor Lal was like, hey, if you can do this, we can use it to measure soil carbon. And so we've started working with him. We sponsored a postdoc with Professor Lal's lab. And the postdoc is then looking at, we've seen a lot of very good progress on this work. We published a first paper, but it's still ongoing work, where we then used a similar technique to then start using a smartphone to start measuring soil carbon. Because if you can do that, a farmer can then start taking much better decisions for the farm. So this is an active project that we're doing with Ohio State University. And around soil carbon modeling, the other new work that we're doing, this is work with Rothamsted University and Glasgow University in Scotland, where one of the other questions we're looking to answer is, with soils are not well understood. So if you look at soils, soils typically have three key properties: the physical properties of soil, that is how it feels; the chemical properties of soil, the chemistry of the soil, the NPK, the nitrogen, phosphorus, potassium; and the third is biological properties of soil, the microbes and bacterial population. People understand the physical reasonably well. The chemical, people try to build models, but the biological is totally not understood. One question that people often ask is, suppose I have a farm. If I do certain practices, like I do tillage, I plant a certain particular type of crop, I apply chemicals, what will be the soil properties at the end of the planting season? Or based on that, you could then start doing soil treatment. No one really understands it. There are process-based models, things like DNDC or DASIN, that have been developed by the soil science community, but people know that it is not super accurate. Now that soil carbon is becoming more and more important, and there is a commercial case around it, there are a lot of startups that have come up, and a lot of startups are looking at it in the other direction. They're saying that, well, forget all the scientific simulations and models that have been built. If you give me enough data, I'll just use AI to build these models, which is one way to do it. The approach we are taking is a different approach. What we are saying is, if you have given the simulations, then you can use that as a starting point and then use causal machine learning to build a kind of a soil knowledge graph like what you're seeing on the right. So you use simulations to build a first knowledge graph. Once you start getting data, you use that data with causal ML to start enhancing the knowledge graph, to start making more accurate predictions for soil in that particular region. This is one of the active research areas in the group as well right now. That is, how do you better model soils? So with that, I wanted to conclude. I talked about data-driven agriculture as a new concept, the impact on climate change and agriculture, the relationship between that, and how can you help agriculture not just reduce the emissions, but help farmers adapt to climate change. And in addition to that, how can you help agriculture actually potentially be a solution to climate change? Thank you.
Fantastic talk. Thanks so much, Ravir. So let's open the floor for questions from the audience. Any question from the audience? Anish, please.
Yeah, Ravi, thank you. That was really quite a tour, quite a journey, and a really impressive set of things you've shown. I had 2 or 3 questions. One was, you've had all these experiences of sort of deploying, the white spaces networks, the LoRa networks, the 5G networks, just from a non-recurring cost perspective. Where do you think we are in the space of knowing which models work well? Is this what are things which seem to be affordable and sustainable on the deployment of the comms infrastructure, if not the sensing infrastructure?
Yeah,
and then perhaps I'll have a few follow-ups based on what you've learned.
Yeah, a great question, Anish. And, we are still at the starting point of deploying this infrastructure. A lot of the rural communities still don't have the infrastructure. And the challenge is that, for some of the biggest operators, they're not incentivized to do these deployments in these remote sites. We've been experimenting with all of them, as you said, right? With LoRa devices, with white spaces, with 5G, with space, looking at all of them. And right now, the way I think of it is that it's going to be a hybrid of all of them, depending on where you're deploying it, what the conditions are, what's more affordable, like for a smallholder farmer. And in addition to that, what's also important is what incentives are available for people in that region. Incentives being subsidies from the government, to having the right, maybe it's provided by an insurance provider or a loan provider. They help with the infrastructure. If you have zero support for infrastructure, you'll go with something which is lowest cost, but the quality would be lowest as well, right? You might just go with a LoRa deployment, but all you're getting is a narrowband communication link. You're not adding any other data services, like, for example, sending camera data and all of that stuff. So that's the state of the art right now, where, depending on what incentives are available, you cut corners and make sacrifices to provide some sort of connectivity. Like, with space, we are again doing space IoT, providing full-fledged space communication, like what Starlink is doing in the middle of a farm, is going to be super expensive. We don't expect farms. So that's why one of the other things I try to advocate for is at different forums where I participate, be it in the FCC USDA Precision Ag Committee or the NIST IoT board or advisory board. I basically try to push for some policies and subsidies. Like, the government, they subsidize different things in a farm. They subsidize seeds, they subsidize chemicals in a farm. Why shouldn't they subsidize data-driven agriculture or subsidize comms? And I think the policy side of it could really drive that shift towards treating farms as first-class citizens to be able to bring broadband to every farm. That's not happening right now. Right now, we are cutting corners based on subsidies, based on how much the farmer is equipped to deploy. The farmer will put in a different level of investment, richer. But, this really increases the divide in agriculture. Like we talk about the digital divide here, the farmers who are already rich or who are already doing well, they are the ones who will be able to benefit most from all the data and AI. The farmers who are disadvantaged, who are in remote sites, who are small, are the ones who will suffer more. The divide will keep getting worse. So that's one thing which I think as subsidies need to be there. Technology wise, I think it's a hard problem too. How do we bring affordable broadband internet everywhere? Let's make it just like, Wi-Fi has become affordable for most people. But Wi-Fi is just, the very last mile. How do you bring such broadband connectivity to farmers everywhere? It's still, it's a technology problem. I think it's a business problem. It might lead to new business models. It's not just about providing connectivity. Maybe people will come up with ways to couple it with insights. Connectivity plus insights is what one should sell, not just connectivity separate, insights separate. And it is a policy problem as well. So that's where things are. I think for farms that are tens of acres or more, and especially if they are doing the cash-rich crops, I think the business models are much easier. It's for the smallholder farmers where it becomes super challenging.
Right. Is it okay if I continue with a few questions?
Feel free to ask questions.
Sure.
Yeah,
so Ranveer, just before we get to connectivity and insights, on this business of deployment, there's a delicate dance between, say, cooperatives being incentivized and sustaining themselves for deploying and managing, and sort of maybe even trusting some of the big companies to come in and sort of help you with private installation. I'm assuming some big companies will be really interested in private 5G networks en masse. So is there any success stories on which models tend to sustain in different states or different countries?
So in the US, a lot of our effort, for example, we are working very closely with Land O'Lakes on helping bridge the connectivity gap. Land O'Lakes is a cooperative, and it's through them they're leveraging some of our technologies and working with other partners to bring insights and connectivity to their cooperative. So that model, I think, is sustaining because it's coming from a cooperative. It's farmers who are leveraging the data and then bringing the benefits back to the farmer population. I think that model is a good model, which we can which works and sustains. The other model could be from bigger companies, but that's something we like. Other bigger companies like the input providers. They could try to take a stance, or I won't count Microsoft as one of the providers because Microsoft is not an agriculture company. Even though we are a big company, we are not an agriculture company, and we don't sell technologies directly to farmers. So I wouldn't count us. But other agricultural companies, one could look at those business models of them providing the connectivity. The insights is something where there are various companies. There are startups. I serve on the advisory boards of some who provide insights to farmers. There are big companies who provide insights to farmers as well. And they're all doing reasonably well. So I think, but then again, they're all for medium to big farmers, not the smallholder farmers. There, I think it's very, very early. There are some interesting models of what a few companies, like for example, in India are doing, or in sub-Saharan Africa, there's one in China as well. But I think it's still early to say that it's successful. Right.
So maybe I'll ask my last question and see if we'll have time for the middle one. So, this point about insights, where are we in the trust developing for these models? I can imagine, are even big companies at a point where they have some confidence in the benefits of and the costs associated with adopting, these insights and these models?
You're asking great questions, Anish. And, this one is a very interesting question too. So, how do you know how well these models work, and models work in different scenarios, right? So that's a very important question. One of the things that we are doing at Microsoft, our thesis is that, AI is not going to replace a farmer. Our thesis going into this is that farmers, they know a lot about the farm. Some of them have been farming there for, like decades or generations. Farmers, they know about the farm. So rather than replacing a farmer, we are trying to augment a farmer with data and AI. Because, the farmers, even though they know a lot about the farm, a lot of decisions they make is based on guesswork. Like when to plant, when to harvest, when to irrigate, where to fertilize. All of this is based on guesswork. So we want to replace that guesswork with data and insight. So our goal is to augment a farmer's knowledge with data and AI. And towards that, we are providing the insights. All the insights are in that context. But to that question, we do look at different areas like what it's trained on, and we have all of these responsible AI initiatives in Microsoft where we look at bias in the data sets and all of that. Going into it, we want to make sure that we are clear about how it is trained, and we have how it is trained, what the data sets are. We do look at that with respect to when we talk to a customer about any of the AI models that we present to them. So that's where it is. If you ask whether it's good enough, I don't think so, because we don't have data from a lot of the small farms, and we make it clear that hurts the performance of the fact that one of the biggest problems for data-driven agriculture is the lack of good, reliable data, and this becomes even worse for smallholder farmers. If you train it on big farms and try to make prediction for a small farm in sub-Saharan Africa, it won't work well. And that's an open problem. So with respect to that, we do flag it that this is the error, but it's not as accurate as what you could get in farms here. So that is a state of the art. So I think we could be doing more, and especially with large models and stuff. So there are interesting things happening even with large models and like with LLMs and even with, for example, GPT-4 and what we are doing a lot with these large models. Some of the things, for example, we are doing in India is there's this other AI for Bharat initiative through the Bhashini work where, this is how do you convert the regional languages and how do you translate them to, say, English or English to one of these regional languages. And that is a hard problem. And there, while GPT-4 does a good job, if you get the local data sets, it performs much better. So this is one of the results that one of the researchers at Microsoft has shown in India. So of course, the better data you get for these emerging markets, the models will be much better. So I think we need to focus collectively on getting a richer data set to drive these models.
Yeah, thanks. Well, okay, I feel guilty, so I'll hold off my last question. We'll see what others want to ask. But thanks for the answers, yeah.
Thanks, Anish.
Any other questions from anybody else from the audience?
I'm assuming there are students too, so in the audience, right? So students, feel free to connect on LinkedIn. Would love to stay in touch. And yeah, hopefully this is one other area where you can apply AI and IoT. I'm assuming all of you work in the IoT and AI space. So think of this as yet another application, and a hard one. I think this is one of the hardest ones to impact, but the most impactful if we can do it right.
Yeah, I do hear a lot of challenges, but these challenges are exciting opportunities as well. So
yes,
yeah.
Wonderful.
So Anish, do you have any questions? I think.
Yeah, well, maybe I'll squeeze in my last one, and
Sure.
I don't know how much time you have, but historically, total cost of ownership sort of got dominated by the recurring cost. You would think that buying that PC was high, but not really. Buying that program initially was high. It ended up just that the recurring cost. So, and you've shared these stories. Yeah, you can reduce the comps by doing edge compute. Maybe even the first mile, white spaces. What's the recurring cost there? But maybe these models are updating. Maybe these models are in a paid for service model because they're continuously evolving. What is your sense? Is the cost in this business going to be dominated by the recurring cost? Or is that somehow going to get contained for there to be real impact?
So this is just my guess, my hypothesis, Anish. I think it's going to be the recurring costs will be there, and mostly to keep the models up to date, to keep the infrastructure up to date. So we cannot get rid of recurring costs. Recurring costs will be there. My take here is that, with these costs, we need to deliver value more than the costs. That is, the farmer should either be increasing their productivity, that is making more money, or reducing costs using less chemicals and so on to be able to pay for the infrastructure. That's the assumption with which we are going in, even for the recurring costs as well as the CapEx is something that might still we need to work. That's why I think the subsidies will come in, but over longer term, the infrastructure should pay for itself. If it is not paying for itself, I think we are wrong somewhere. We are not, then this doesn't add value.
Exactly. Yeah.
And that's the point that's the point we want to get the solutions at, where the infrastructure is a fraction of the total amount of value it's bringing to the grower. And that's where I think we need to get to.
Right. No, totally agreed. Yeah. Great. Again, thanks so much, Ranbir. This is great. Enjoyed it.
Yeah,
Yeah.
we like
Probably I'm gonna ask the last question.
Yes,
I'm pretty curious because the cycle of farming is long, right? Normally like a year, and it takes a longer time to see the outcomes of either applying AI or for the farmer to see the outcomes. So I'm thinking how to expedite this, right? To see or to interact with this much faster but short way, so that we can maybe convince more farmers to use this technology, right? So yeah, that's do you have any thoughts on this, or how do you see?
Yeah, this is what farmers say, I get only 40 times in my lifetime to try something. So in this 40 times, it's not like code where every minute you could change it, or any other software. It's a different business where you have very little, like you have just 40 shots at something.
That's
we
right.
need better simulations at it. One of the things that indoor farming is one way to try to expedite things. Simulations is something we need. The simulations are not very accurate. The more accurate simulations we can do, the better we can do it. Or trials at scale, being able to run these trials at scale is another way you could potentially do it. Like you have research farms in different places. You'd run something in Ohio, run something else in another farm next to it. That's the way people do it, but that's not as scalable either. You can't really, in simulation, you can change all the parameters. The simulators are not super accurate. So this is an open problem. If there is someone looking to go after, digital twin kind of an infrastructure, simulator, emulator for farms, we build some things. If someone wants to do it, we're happy to provide all the tools that we are building. This is not an active project in the group, but I think this would be super, super valuable if someone wants to go after it. Yeah. Because you're completely right. Without such a thing right now, we are limited with how much we can evaluate. We have to run things for several years before we can claim how much improvement we get. If you could run some of this at a faster scale, it would be much easier, much better.
Yeah, I agreed. I assume there are no further questions from the audience. If that is the case, we're going to conclude this seminar today. Thanks so much again, Ranbir, for taking your time and giving us a wonderful talk. We are very excited about this agriculture, AI field. Hopefully, we can work together in the future.
Thank you, Me, and thank you, everyone.
Thanks so much. Yeah,
bye.
Thank you.
I see Longview there too. Yeah, thank you. Bye.
Yeah, bye, everybody. See you next time.
See ya.
Thank you.